you guys did for the coursework. It's super helpful to read that and to understand, what are the pain points for you guys in terms of online learning on that sort of stuff. So you may see small things being mixed up over the next few weeks in response to that feedback. But again, a lot of it is just super useful for us to know so we can improve, as lectures and that sort of stuff. But before we get started, are there any questions about, say, the homework or the course or about where we're going as an organization? Or any concerns? Okay, well, if not, then I'll hand it over to Jamie.
Great, thanks, Kevin. Can everyone hear me all right?
Yep, can hear you fine.
Great. Okay, and apologies if the video is not working perfectly. Having some slight technical difficulties this morning. All right, so we're going to move on to another set of things that we can use for classification today. Last week, you'll remember that we talked about logistic regression, right, which was our first set, or actually that was maybe 2 weeks ago, where we talked about logistic regression as sort of our first way, our most natural way to take real valued predictions, turn them into probabilities between 0 and 1, and then threshold those to form a linear decision rule to decide between, to make a prediction about future inputs and decide whether or not those should be labeled as +1 or -1. And then we took a bit of not a detour, but we had seen several examples of these sorts of optimization problems where there weren't obvious closed form solutions, right? In particular, lasso and logistic regression don't have closed form solutions for the W that we might want to find, which minimizes our loss function. And so we thought about optimization. We talked about gradient descent and stochastic gradient descent, and talked about how we could use those approaches and what those approaches look like to minimize our loss functions. And I just want to make a point that you can sort of think about regression and classification in many different ways. Here are two, right? The first of which is what we've been emphasizing so far, which is that we can make some assumption about the joint probability distribution between X and Y, and then, pick a loss function, maybe as a function of that assumption, and find a model which maximizes the likelihood of our training data given that assumption, right? And that's often reformulated into a loss minimization problem, right? And that's what we've largely been doing thus far in the course, right? And there's sort of a more, I don't want to say agnostic, but perhaps agnostic way to think about regression or classification, which is one that we'll sort of employ today, okay? Which is this idea that, okay, we have some classification problem. We pick a loss function, right? Not necessarily thinking much or at all about the joint distribution between X and Y. And then we pick a set of hypotheses, right? Or possible decision rules. And then pick a function from that set of hypotheses, which minimizes our loss function on training data, right? And this second viewpoint is the one that we'll focus on today. Okay. So just reminder, right? I'm just giving you, right? We just did exactly this for logistic regression, right? We did an example of the former, right? But we made this assumption that the probability of Y given X and W had the following form, right? And that's a maybe pretty natural assumption, but it may or may not be correct, right? So it may be the case that some other data generating process actually governs the relationship between X and Y for our particular data set. right? So if these assumptions are wrong, right, then some of the guarantees that we argued about earlier don't necessarily hold, right? So we'll think about another way to pick linear decision rules today. Okay, so I want to, we'll be talking about loss functions a bunch today, and we've talked about them throughout the class, but I want to sort of emphasize some of the loss functions we've looked at, because we're going to come back to them in a minute, right? So the first loss function we thought about was squared error loss, right? Which is this nice orange line on the plot we have here. We talked about logistic loss, right? Squared error loss was what we talked about when we were talking about least squares. Logistic loss was what we were talking about for logistic regression. 0-1 loss, which actually isn't pictured here, but I'll draw it in now. 0-1 loss is just saying we get loss of 1 if we make the wrong prediction, and loss of 0 otherwise. Right? And that's in large part what we care to optimize, right? That's sort of, if what we're trying to do is say that we want to minimize the number of misclassifications we make, right? 0-1 loss is a natural way to describe that, or it is the most direct way to describe that. It has plenty of problems, but it certainly captures this idea that what we want to do is minimize the number of mislabelings we might see. And I'm going to introduce a new loss function today, which is known as hinge loss, okay? And hinge loss is somewhat different than the other losses we've talked about so far in a couple of ways. One of which is, so hinge loss is this maroon line in this plot here. And basically what it says is, okay, we're going to have some prediction, right? And I want to penalize that prediction in a particular way, right? If I make the right prediction, then I'm not going to get a penalty. But if I make the wrong prediction, I'm going to sort of think of a prediction not necessarily, so there are several ways to think of the prediction, and thinking of it either as a binary thing or as a real valued thing. But I'm going to care about sort of how wrong I am, okay? And we'll see more precisely what I mean in a moment. Okay. So if we have, the sort of canonical way to think about the hinge loss is the following. Okay, so suppose we have, a bunch of positive and negative examples that look like so. And if I wanted to ask you which of the following lines is the best, right? What would you say? Anyone can answer that question.
Maybe one guess is like the one in the middle, maybe?
Yeah, right? So this one, right? And it's not totally clear why, but sort of our intuition suggests that maybe the one that sort of keeps the data as far apart from the decision boundary as possible might be good, right? And there are lots of ways to formalize that in terms of like assuming some kind of symmetry across the data generating distribution for the two different classes, all of these different things. We won't focus on that today, right? But there are a number of different reasons why this sort of middle one is best, right? And we'll talk a bit more about that for the rest of class. Okay, so the middle one, if we want to be somewhat more formal about what we mean by this middle one, what we mean is the middle one, right? This is the middle. Middle in high dimensions is a little more, if we weren't just in one dimension, middle seems a little bit harder to define, right? What we mean is when we draw the line And then we draw basically parallel lines to that separator in a way that puts as much space between the decision boundary and those lines, but continues to keep all of the positive examples on one side and the negative examples on the other side of those two parallel lines, right? Then we call the distance between these two lines the margin of this classifier. Okay, so the margin basically measures how far the nearest data points are from the decision boundary. Okay, and for a number of reasons, picking a classifier, picking a linear decision rule, which keeps the data points we have visible, separated and as far apart from the decision boundary as possible, is generally a good idea. So if we want to, presumably we won't be given these parallel lines for free, right? If we wanted to actually measure what this margin is, right, what we would do is we would say, okay, if we have a particular decision boundary, right, what is the distance between this decision boundary, this hyperplane, and all of our different data points, right? And for example, we could be thinking about x naught, and the distance between x naught and this hyperplane, right? We just have to think about projecting x naught, right? And in general, if what we're saying is the distance between x naught and some hyperplane, that's equal to the minimum distance between x naught and any point on the hyperplane, which is equal to the distance between x naught and x naught's projection onto that hyperplane, right? Some basic linear algebra here. And the way projection is defined means that the distance between x naught and x naught tilde, right, is just equal to, right, this is just projecting x, so like, right, so the distance here is equal to this one, and because we can pull out this norm of w squared to the outside, and then because x naught tilde is the projection, is a projection on this hyperplane, this simplification takes place. Okay? So the distance between x naught and its projection onto this hyperplane is simply equal to, first, applying the linear function to x naught, and then normalizing by the magnitude of w. Okay. And the reason there are several ways to think about why the magnitude of w comes into play when thinking about sort of the distance between x naught and this decision rule or the decision boundary. But the simplest one, think about the following, right? So if we scale w, right, if we just like make w a longer vector in exactly the same direction, that doesn't actually change the distance between x naught and that linear decision rule that w defines, right? So this is just sort of, that's an intuition for why we have to normalize by the L2 norm of w. Okay, so the point is, if we want to think about picking a decision rule or a hyperplane which has large margin, what we want to think about is maximizing the minimum distance for any point on either side of that hyperplane, right? And that'll be equivalent to maximizing the margin. Okay, so in slightly more mathematical notation, right, or just formalizing what I just said in words, right? Generally, the way we can describe the problem we were just talking about is that we want to maximize our margin subject to our margin actually being a lower bound on the distance between any point and the hyperplane. right? And this yi actually appears here, right? Because we care about points arriving on the right side of the decision boundary. Okay. Any questions here?
Yeah, I have a question.
Mm-hmm.
Is this only relevant when we can perfectly bisect
Yes.
our data with a hyper?
Yes, yes, yes. Right. So we started with this sort of toy example that I've continued to like draw additional pieces onto, right? But as you can see, and as I think that was Brendan, I can't see on the current screen, but Brendan asked, what we see here is that we have points that are separable by a hyperplane such that all of the positive examples lie on one side and all of the negative examples lie on the other, right? And we'll talk in just a minute about what to do when that isn't the case, right? Because that's overwhelmingly not the case in practice most of the time. Okay, so before we do that, let me make one quick reparameterization, which is so this term is a little funky, right? One thing we can do is we can reparameterize it and say, okay, we actually want, the only thing we've done here is we've replaced gamma by the L2 norm of W, right? And the way you can look at that is just multiplying both sides of the constraint by the L2 norm of W, and then doing some small reparameterization. These two are equivalent optimization problems, right? So the second one is just saying we still need to have our margin, right? But this margin somehow never explicitly takes into account the norm of W, which is nice. And then we want to minimize the L2 norm of W squared, right? And one of the nice things about this reparameterization is that this distance, the margin can be written in this way, okay? Where W, again, reminder, was the vector here. Okay. So there are a number of reasons you might want to do this. The simplest of which is it doesn't explicitly, this formulation has one fewer variable, right? So one fewer degree of confusion. And it's explicitly just saying what we want is we want a short vector, right? That separates our data points and keeps some distance between them, right? Okay. So you might ask how we could optimize and actually pick RW, which minimizes its L2 norm subject to having this margin, right? And we've talked about a few different methods in the past few classes that would be appropriate here, right? Stochastic gradient descent would work well. Standard gradient descent too. You could also solve this using some kind of quadratic or other convex programming problem approach. And coordinate descent in the dual, which we're not going to talk about what I mean by the dual today, would also be appropriate. Okay, so if you're asking how you actually find this W subject to this constraint, all of these approaches will be appropriate. Okay, so far we've been talking about examples where we can draw a linear decision boundary such that all the positive examples are on one side and all the negative examples are on the other. And that's nice. But that's rarely the case in practice. Certainly for, if someone hands you a data set, the world would be a much easier place if it was ever the case that they handed you a data set and a classification task for which like a simple linear decision rule already did a perfect job classifying, right? That's never the case in terms of what we generally see. And when that's not true, we basically have at least two options, right? One of which is introducing slack variables into this optimization problem. And I will go into that in more detail in a moment. And the other, which we talked about when we were talking about linear regression, and maybe we've actually come back to it and revisited it several different times, is the idea that we can basically take our initial features and we can basically do interesting combinations of those features and lift our data into a higher dimensional space. And then maybe in that higher dimensional space, we'll actually see something which is linearly separable, right? Okay, so, right, and the shorthand for what Brendan asked about before, right? If does there exist a hyperplane that actually separates the two classes, is this term linearly separable, right? It's a very intuitive phrase, but that's just the one that's generally used. Okay, so we'll start by talking about introducing slack into this optimization problem, right? Because even if you lift to a higher dimensional space, usually there won't be a reasonable higher dimensional space for which your data is perfectly linearly separable. Okay, so when our data is not perfectly linearly separable, right? Presumably you all have some like geometric intuition for what this means. It simply means that if we drew the sort of the outer boundary around the set of red points and green points, right? If we drew the convex hull around them, right? Which is just the smallest convex set that contains all the red points, and then separately the smallest convex set that contains all the green points, that those intersect, right? That they have non-empty intersection, right? That's what it means for data to not be linearly separable. If that's the case, it's still natural to ask how we might want to pick a linear separator. But it's no longer the case that all of the points will be, at least a margin away from the decision rule. In fact, not all of the points will even be on the right side, right? So the change to the optimization problem is as follows, right? Specifically, we'll be thinking about a linear decision rule, which may be violated by some psi of I. Zeta? Is that psi or zeta? Kevin, what Greek letter is that? I can't actually tell.
C.
C. There we go. That's not one I use very frequently. Okay, C. Okay, so I might call that Z because it's easier to say. Okay, so it may be the case that we not only violate the margin constraint, but we're actually on the wrong side of the decision boundary by some Zi for each example I. But we likely want to limit the amount we're actually allowing the sum of those Z's to violate the margin. Okay, so as is drawn in this nice little picture, right? What we have here is we have a margin where the decision rule is saying red points should be on this side and green points on this side. Right? But we have some red points on the green side and green points on the red side. And the way we penalize our optimization for such points is as a function of how far away those points are from not just the decision boundary, but actually this sort of thing we're still thinking of as a margin, right? It still is a margin. It's just that there are some violations to both the margin and to the linear decision rule. Okay. Right. And also notice that we're not only penalizing the points which are misclassified by this classifier, we're also penalizing points that are on the right side that are violations of the boundary, or of the margin rather. Okay. Okay, so we haven't talked about this explicitly, but a really nice property of support vector machines, which is what we're talking about now, is the following, right? So if you're looking to define linear separators that maximize margin, right? If we're first thinking about the linearly separable case, right? There's something really elegant about, that we haven't explicitly pointed out yet, which is that there are only a couple of data points which seem crucial for actually defining the hyperplane W, right, or X transpose W plus B, right? Namely, the points which are closest to the margin. Right? Those are known as support vectors. Okay? And the point is that, like, if those points were to move closer to the decision boundary or further away from the decision boundary, right, they might actually change the margin maximizing, the margin maximizing decision rule. On the other hand, if any of the other points were to move, right, if any of these points or these points were to move, right, and by move I simply mean like if our data set had different points instead of those, we wouldn't choose a different decision rule unless those points suddenly became the closest points to the margin. Okay, so maximizing the margin has this really elegant interpretation of basically, we have a bunch of data points, but we really only need to define, we really only need a very small number of data points, the ones that are closest to the decision rule, to define the decision rule that we actually care about. Okay. On the other hand, if we're thinking about the linearly, the case where we are no longer thinking about something linearly separable, right? We have more data points which are sort of defining the cost of our decision rule, which are namely all of the points which violate the margin condition, right? All of these which have slack variables greater than 0. Okay, so in this case, maybe that's not the best color for this. Let's do this. Okay. Right. So in this case, the support vectors have psi greater than 0. Okay. All right. So, right, we just defined, or we just said what the support vectors are in both of these cases. In the former case, it's just the points which are closest to the decision boundary. And in the latter case, they're any point which violates the margin condition, right? Which you can see the former is actually the limit of the latter if points are getting closer and closer to satisfying the margin condition. Does anyone have any questions?
Yes. How many support vectors do you decide you want?
That's a great question, right? And I've sort of alluded to the idea that you might need very few. So it's not so much a decision of how many you want. It's instead that in 2 dimensions, you really only need 1 point from each of the 2 red and green classes to define W. And in the example I drew above, or at least in the linearly separable case, right? In the example that we have drawn here, there are actually 2 green points which are equidistant from the decision boundary, right? But it's sort of either one of those would be sufficient to define W. And in general, in D-dimensional space, right, you'll need a number of points that depends linearly on D to define the hyperplane. Okay. So that's like you can do a little bit of like geometric reasoning about that, right? Basically, what you're thinking about is the convex hull of the 2 sets of points, right? And you're picking a hyperplane that separates them in this former case. and you can reason with yourself that, sort of to define that hyperplane, you only need the points on the hyperplane which are closest to it. And that uniquely defines a hyperplane if you have a number of points which is d+1, where you're in d dimensions. Okay. When we're not in the linearly separable case, right, we suddenly have a bunch more things which we're referring to as support vectors, right? They're now all of the violations of the margin constraint, right? As opposed to the sort of tight constraint, the points for which the margin constraint is tight. So there might be many more, right? And that doesn't depend in so natural of a way on the dimension. It depends much more on sort of how close to linearly separable your original problem is.
Does that mean you're like, do people say that they're trying to minimize the number of support vectors?
No. Yeah. So I mean, right. I understand why some. Let's talk not about the linearly separable case, because that's like sort of there's a fixed number you need there in a certain number of dimensions. In the non-separable case, it's not that people are trying to minimize the number of support vectors per se. They're minimizing the sum of the violation of the margin condition, which is related, if all of the violations had sort of equal distance from the margin constraint, that would be equivalent. But usually, right, as is in the example that we've drawn here, the margin violations are a very different size, right? This one's big, this one's little, this one's also little, right? So it's not so much that we care about the number, although the number certainly is one thing we care about, right? Because that sort of corresponds to the number of, it has some interpretation in terms of loss, but what we really care about is sort of how long we are. Any other questions? Okay, great. Okay, so we can also think of SVM, right? We were just talking about it as sort of this quadratic program with linear constraints. And like we talked about with lasso and Kevin so eloquently described, we can actually, quadratic programs are kind of a pain. So you can instead write this as sort of a nice problem where we basically we incorporate the constraints into the objective directly, okay? And say that, for any nu, which is just this average violation, or the average violation, it's really more the sum of the violations, of margin, right, of the margin constraint. So for any sum of the violations of the margin constraint, there exists basically a regularization parameter, lambda, such that you can find a solution to the following optimization, which has the equivalent objective value. Okay, so that's just a remark about another way you can think about this particular optimization problem, right? And one nice interpretation that falls out of this is that we're trying to regularize to have relatively small w, right? Sorry, small meaning the norm of w being relatively small. And there are a bunch of reasons we might want that, but the simplest of which refers to, sort of when we were talking about logistic regression, right? In the linearly separable case, basically increasing the magnitude of w was, to infinity would make for, that would continue to drive the loss down, but like w wouldn't be representable in some obvious way, okay? So you can think about SVM as some kind of regularization. So let's talk a little bit more formally about exactly what SVMs are optimizing, right? What they're actually optimizing is this kind of strange thing, where for the data points which are satisfying the margin, we get 0 error, right? We get 0 loss, right? And for the data points which are not, satisfying margin. For the data points which are not satisfying the margin, we get some penalty which depends upon how much we're violating the constraint, right? For violations of the margin. Okay, so notice that there's a yi here, which we've seen a number of different times, right? That's just corresponding to this idea of making sure that we're accounting for the fact that our decision, our W actually places our prediction, our decision rule actually has some sign, and that sign being equal to yi means we're making the correct prediction for xi, in the sense that yi is equal to the prediction, the sign of the prediction that we were looking at before, and otherwise not. Right? Okay, so this is just another way to view the SVM objective, right? And we can actually write it as a sum of individual losses applied to each of our individual data points, right? And we've done this a bunch of times, right? And when we do this, we're actually incorporating this second term. We can sort of divide it by the number of different data points we have and sort of sneak it into the term that has something to do with xi, even though it doesn't depend explicitly on xi. So if you wanted to think about, doing SGD, for example, right, you would need to understand the gradients of this loss function with respect to W and B. And we've written those out here, and it's a good exercise for you to do to sort of walk through these on your own and actually verify that these are correct. Okay, so as I mentioned before, right, and this is one of the really elegant things about support vector machines, the minimizer of this objective function can actually be written in terms of a very few number of training points, and these points are known as support vectors. Right? So this sort of really explicitly brings out the fact that the support vectors are exactly equal to the points for which the margin constraint is violated, and those are basically the ones that actually define the optimization that we're looking at here for SVMs. Okay. So we talked about one example, one way for dealing with data that basically there doesn't exist a hyperplane to separate, right? By introducing slack into the optimization and then trying to minimize the amount of violation on average, the data points we have. The other approach that we'll talk about today is something that we talked about before, right? Which is lifting our data to some higher dimensional space, right? So, right, we can basically take our d-dimensional data and project it up into some higher dimensional data, into some higher dimensional space, or maybe not higher dimensional, but just some different space. But if we think about, some of the ways we talked about this before with polynomial regression, right? One thing that we will notice is that like the feature space can get really large really, really quickly, right? So if we're actually thinking about projecting our data into, into D dimensions, that's fine if D is 1, right? When D is 2, we suddenly see that we need, many more dimensions, right? Twice as many dimensions to represent our lifted data. But if what we do is we think about lifting our data into, degree D polynomials of our original expression of our data, the dimension of our lifted data will grow as an exponential in D, right? And that is, that can be pretty problematic, right? If we start in P dimensions and we think about degree D polynomial representations of our initial data set, or of our initial data representation, our feature space, P to the D gets huge super fast as D grows, right? So, while we can do this, while we can lift our data into higher dimensional space and hope or observe or something else that our data is linearly separable or closer to linearly separable than it was in the original feature representation, even writing down our vector representation in those higher dimensional spaces suddenly becomes pretty intractable pretty quickly, right? Let alone sort of thinking about like computation on those higher dimensional vectors. So how do we deal with this? And this is not a problem, a somewhat funny aside, I was talking to someone yesterday about why support vector machines and the thing I'll talk about in a minute are sort of often taught together. The thing I'm about to tell you about has very little to do with support vector machines directly, right? It's just a general technique that you can use from everything from like clustering to PCA, all sorts of things we'll talk about in class, and also all the things we talked about before. If we have sort of some representation of our data in some high dimensional space, there's a fundamental technique we can use to deal with that in a way that sort of limits our need or gets rid of our need to actually explicitly write down this high dimensional representation of our data. And the fundamental trick is to use something called a kernel. Okay? So a function, K, takes 2 points in RD, right, which is our original space. So remember that these are points in our original space. And it's a kernel for a map phi if, when we think of applying the kernel to x and x prime, which are points in our original space, that's equal to the dot product of first mapping each of the points into this higher dimensional space and then taking that dot product. Okay, so what is this thing, right? This function takes 2 points in our original space, right? Our space before we sort of lifted up our data. So those are low dimensional things. And then produces some real number, which is equal to taking the dot product of these feature vectors that are projected up into high dimensional space by our map, right? So that's really nice because if the kernel can be computed quickly, right? If kxx prime can be evaluated quickly, that gets rid of our necessity to actually write down phi of x and phi of x prime if phi of x and phi of x, if basically the only way we need to actually access this lifted data is through dot products. Okay, so does anyone have any questions about this? I imagine so.
Is there any restriction on the kind of fees you can use, the kind of lifting maps you can use? What kind of fees can you use?
So not all maps will necessarily have like the most natural kernel, right? So I guess the short answer is if you have a map, right, you can certainly define the kernel of that map as the thing that explicitly projects our data into, it projects our data phi into, like with phi, and then explicitly computes the dot product, right? So for any phi, there is a kernel, but ideally the kernel will be able to do that computation without explicitly applying the map and doing the dot product, right? And not all phis will actually have a kernel that doesn't have to do that explicit lifting of our data into the high dimensional representation and then doing the dot product there. Right, so that's a good observation, right? So like any map phi, we can certainly define the kernel of that map, right? But the question is sort of when do those kernels actually have like faster ways to be evaluated than to explicitly use phi to do the computation of dot products. Okay. Good. All right. So, right. Oh, sorry. Go ahead.
I was wondering, is a kernel is the kernel function designed such that for all cases of your data, it would successfully be able to create the dot product of the dimensional space used in the SVM?
I think I don't totally understand your question, but ask it again in a couple slides if I don't answer it.
Okay, thanks.
Yeah. Okay. So I'll give you a couple of examples of kernels, right? So these are some kernels, right? They're functions that take 2 degree D vectors and then do dot products of them, or then basically do some computation upon them, right? And you can think about what are the maps that these are kernels of. Right. You don't really even have to think about the maps that these are kernels of, although it's like a nice exercise, right? You can sort of use the kernel trick while mostly ignoring thinking about this map explicitly, which is kind of a strange thing that I always found sort of weird. But we may come back to that if we have a little more time. Okay, so these are just some functions, right, from 2 points in our original d-dimensional space that produce some real number, right? Because this dot product, right? This dot product is just, these all produce real numbers, right? Remember that k goes from RD to real numbers. And also notice that these don't explicitly have to, they sort of do most of their computation in the d-dimensional space as opposed to in some higher dimensional space, right? They take dot products in d-dimensional space, or here, right? This is something where you take the difference in d-dimensional space and then you look at the L2 norm. And similarly here, right, we're doing some computation in d dimensions rather than in some higher dimensional space, right? And that is the big computational win of using kernels, right? That kernels generally can be written down in such a way that you don't ever explicitly have to think about your data in some higher dimensional space. You can sort of do computations on it in d dimensions, and somehow get the behavior of a higher dimensional space without having to pay the additional computational cost. Okay, so slightly more formally, and hopefully this will answer the question that I had a few slides ago. The way this works, to be more formal, right? The way a kernel trick, this is called the kernel trick, right? I've said use kernels, but that's often called the kernel trick, works in machine learning, this is sort of a template that you can take for yourself, is that you first pick a kernel, right? You pick some function. You then prove that the optimization problem that you're solving, right? In this case, the W that you want is actually equal to some linear combination of your initial data, okay? And then you change your loss function and your decision rule to only access your data. And by data, I mean our XIs, right? Our feature representation. Through dot products, right? The decision rule, right, is generally pretty easy, right? Because, right, if W, right, so usually we're thinking about W dot X greater than or equal to 0, right? Well, this is already a dot product, but it's not a dot product between two of our initial data points. However, because we proved that W can be represented as a linear combination of our initial data points, this is equal to the sum of alpha I xi dot x, right? So our decision rule, once we've shown that our W, the thing we're actually optimizing for, can be written in terms of our initial data, right? Then showing that the decision rule can be applied by only thinking about dot products, right? So here, right, if we're thinking about this decision rule, right? This decision rule, which is the same, right? These two are equivalent, right? The second one only ever touches data points in our feature space through dot products, right? Whereas the former one takes into account the x's, right? And the x's might be in some high dimensional space. Okay. The loss functions we'll talk about in a second, right? How to like actually think about our loss functions as dot products. But the final step of the kernel trick before we get there is to substitute the kernel of xi, xj for any of the dot products that we see in our modified or sort of our rejiggered optimization problem. Okay, so just to go over that again, right? The way to use the kernel trick is to pick a kernel, to prove that the original optimization problem we were thinking about, the solution to it can be written as a linear combination of our initial data points. Then basically rewrite the optimization we were thinking about, where it only ever touches points in RD in a way that involves dot products. Okay, specifically dot products with other points in RD. Right, that's the only place it makes sense to take dot products. And then substitute the kernel for all of those dot products. Okay. So actually, before I go on, did that answer the question from a few slides back?
It does, thanks.
Great, good. Okay, so why is it the case that loss functions, all the loss functions we were talking about before, can sort of naturally be described as dot products of our initial data? Right? So the squared loss, which we talked about first, right, just looks like xi transpose with dot producted with W, right? And if we show W is equal to the sum over I of alpha I xi, right? Then just like we talked about a minute ago, this loss is easily represented as dot products between xi and xj. Okay. Similarly here, right? If we show the same thing for logistic loss, right? If we show the minimizer of logistic loss actually is equal to some linear combination of our training data, right? Then xi transpose w can be written as a dot product of xi transpose and alpha I xi, right? Which is just equal to dot products between xi and xj. Okay. 0, 1 loss has the same property, right? If we can write that w has the same ability to be written as the dot product of some number of vectors. And hinge loss, which is the one we were talking about for support vectors, right, also has the property that it only ever touches xi transpose when it's taking its dot product, with w. And the question is, you know, in all of these cases, like the loss functions are easily representable as xi transpose as a function of xi transpose w, right? That's the only place where our xi's are written down in the loss function. And so all of this, right, our ability to use some kernel trick here, A, we need a kernel, and B, we need the ability to show that the w which minimizes these losses can be written as this linear combination of our training data. Right? Okay, so let's think about SVMs, right? Specifically, SVMs had this nice, we want to think about picking a kernel, which we're not going to talk about explicitly here, but we gave some examples a couple of slides ago. We want to prove that w is equal to some linear combination of our x's. Okay? And I'm going to give you some intuition for why this is true, right? And maybe we'll have you do something a little bit more formal for this in a moment. But okay, so if we were thinking about earlier, right, when we had data points on both sides of just making sure that there are a couple of data points of each color on both sides. Okay, when we were thinking about data which was not linearly separable, right? What we said was the support vectors were those data points which violated the margin, right? So certainly any points in between the red line and the gray lines are violations, right? But also any points that are the wrong color on either side of this as well, right? So informally, W is defined by violations of the margin, right? These are the only points that actually are affecting the loss function directly when we're thinking about W. And they're actually affecting the loss of W as a function of how much the margin constraint is violated. So you can think about, right, the C's, right, the violation. As an alpha, right? Or something close to it, right? And then convince yourself that basically there's some way, maybe I'll just say that these are related, okay? The alpha i's, right? The way that the W can be defined in terms of our data, just as some linear function of our data, is to think about how much these points are violating W. Okay. All right. And this W is supposed to be the one that's the argmin of hinge loss. Okay. So if we want to use the kernel trick for SVMs, we need to pick some kernel, which we're sort of punting on for the moment. We sort of waved our hands and given some intuition for why the hinge loss minimizing W can actually be written as a linear combination of the support vectors, right? The points that violate the margin. And then, right, we want to change the loss function or the decision rule to only access data through dot products. Okay, so we already talked about, right? We already talked about how to do this here, right? So hinge loss, right? We did before, and the decision rule, right? As we talked about before, is also very easy because the decision rule, which was just W transpose X minus beta being greater than 0, right? This is just equal to this alpha I xi xi transpose X sum over I minus beta greater than 0, right? I'm just taking this proof. I'm just taking the fact that we now know our W can explicitly be represented as the linear combination of our data and using that and substituting it in here to make our decision rule a function only of dot products rather than of points in our d-dimensional space. Okay? So then, if we actually wanted, if we had a kernel in mind, right, the decision rule then becomes alpha I, the kernel, times X I transpose X minus W minus B is greater than 0. And similarly for the hinge loss, right, we could do the similar expansion where we explicitly put our kernel here, right? Substitute our kernel. Okay. Do people have questions about that?
I asked this in the chat, but I guess I'll just ask you directly. So once you kind of do the kernel trick and you do SVMs, right, and then you get your decision rule in the high dimensional space, is it possible to visualize that in your original dimension space?
Depends on the kernel. Usually yes, but it won't be a linear function, right? Usually, right? So we haven't actually given you any of the nice pictures, which like some slides on so also I want to be clear that like kernel trick SVMs are sort of two things that can be used together, but like, you know, you can ask like if you're using the kernel trick for an arbitrary thing, can you sort of visualize the decision rule in your original space? And the answer is, yeah, you can draw it, right? But it's not going to be linear, probably, right? Because otherwise, why are you using a kernel?
Of course, yeah.
Right? So lots of the nice visuals and like some other representations of these slides that I was like iterating through is there are kernels that basically take, suppose you have a bunch of points sort of contained within a circle, right? And those are all in one class. And then you have a ring around them from the other class, right? That's not a linearly separable set of points, right? There's no linear separator in R2 that does any good job at all in terms of making classification decisions. However, there's a really nice kernel, right, which basically lifts that and allows you to separate those points perfectly, right? And you can then draw, you certainly can draw to the decision boundary in R2, right? It's simply drawing a circle around the inner ones that keep the sort of ring of the second class outside, right? But it's not a linear function.
Right. So basically, like my idea, I guess, so far is like basically you're using kernel trick to find some nonlinear decision boundaries, right? And so instead of finding a nonlinear boundary in your original space, you just lift it to some high dimensional thing and find a linear thing there, which I guess translates to doing nonlinear things in your original space. Right. Okay.
Right. So yes. Yeah.
Cool.
Okay.
I had a really quick question. This
Yeah.
may be kind of a dumb question, but I don't quite get the difference between a kernel and the map phi that you are like some kernel K is a kernel for a map phi. Could you just quickly explain that again? Sorry.
Sure. So what this means, right? Kxi is equal to phi of xi dot product with phi of xj. And the point is that like xi and xj are in our original d-dimensional space. We're sort of treating that as like it's some low dimensional space or reasonable dimensional space, such that at least our data can be written down. Phi is in maybe some like infinite dimensional space, right? It could be some very high or maybe even infinite dimensional space. So these are now vectors, right? These are vectors in RP, right? And the kernel function just says, given xi and xj, I can tell you what the dot product of phi of xi and phi of xj are, right? For any, right? And that can certainly be computed by like explicitly mapping xi and xj to phi of xi and phi of xj. But there are often more efficient ways to do that. Is that helpful?
Yes. Okay. I get it. Now I can understand why this is mapping to higher dimensions. Okay.
Great. Anybody else? All right. Okay. So I'm going to talk a little bit just to give you some sense and to sort of try to break you from the notion that like SVMs and kernels are like somehow intricately connected in a way that isn't true for some of the other things we'll talk about and have talked about so far. I want to talk a little bit about the kernel trick for regularized least squares, which is a problem we already talked about, right? Or, you know, in this case, right, we're thinking about ridge regression, right? Okay, so why is it the case, right? The kernel trick sort of, we're going to punt on picking a kernel K. But the next step is to show that the W, which actually minimizes our loss, can be written as a linear combination of our initial data points, right? And why is that the case? So the short answer is that you can actually write out this optimization this way, right? We know the form of the minimize, right? For ridge regression, we sort of have a closed form solution. Right? And, you know, it's good exercise to show that the closed form solution is equivalent to this. Right? So this closed form solution, this term, right, actually has some nice format, which at least so far is looking like it might be describable in terms of, we've just reparameterized, right? So we basically said we can equivalently write this optimization problem as this one, okay? And doing so will tell us that what we want to find is the vector alpha, which minimizes y minus k alpha squared, the L2 norm of that squared, plus some regularization term. Right? And this regularization term, right, like we certainly had some intuition for why we were regularizing when we were thinking about least squares without thinking about the kernel explicitly, right, as we notice here, right? this is just doing the substitution. Right? Sorry, I can't today. Okay, so this is just doing the substitution of the kernel for the dot product. But we had some intuition for why we regularized when we were thinking about least squares, right? There are instances in which you would overfit to your data set, and you might sort of want to bias the solution of your optimization towards having sort of smaller W, right? That's what ridge regression was doing. But when you're thinking about kernels, right, there's a good reason to think about regularization, which sort of has some separate interpretation from the one for least squares. Okay? And the reason is that you can easily overfit, right? And we'll talk a little bit more about that in a minute, right? But for many kernels, it's going to be really easy to overfit our data, much easier than finding, a linear function in d dimensions, right? And the intuition behind that is that, our kernel, right, is doing something. It's not maybe explicitly, if it's a useful kernel, it's usually doing some computation that represents dot products in high-dimensional space, right? And even if it's not explicitly operating in that high-dimensional space, the fact that it's able to express dot products in that high-dimensional space suggests that it's maybe a complicated enough beast that it might act a little bit more like that high-dimensional thing in terms of how well it'll generalize. And I'm saying that in the loosest possible sense because it's not really the case that you have to worry about that quite as much as I'm suggesting, right? It's not the case that you'll always have you'll always have to suffer generalization that's sort of a function of the higher dimensional, like the P that we were talking about before. But there's some sense in which lifting to this higher dimensional space doesn't come totally for free. Okay, so just to remind you what we've talked about so far, right? We're thinking about support vector. We were talking about support vector machines, right? They're another way to do classification, right? Largely, we were talking about SVMs directly in terms of linear decision boundaries, right? And they optimize this weird thing called hinge loss, right? Which has the following shape, right? Which basically says if you don't violate the margin, you have zero loss for any data point that doesn't violate the margin, and for any point that violates the margin, you get this doesn't look like it's at a 45-degree angle. You incur loss, which is directly equal to the amount by which you violate the margin. Then we talked about the fact that all of the loss functions we talked about so far in class can be written as these nice dot products of W transpose Xi, which sort of suggests they're ripe for kernelizing, right? And kernels avoid sort of explicit representation of high-dimensional vectors, right? They allow us to compute dot products of high-dimensional vectors, or at least taking X, mapping it to some high-dimensional vector 5X, and taking the dot product there. And the way we actually kernelize a machine learning algorithm is that we pick a kernel K, right? And K of UV, or X prime, should be equal to phi of X dot product phi of X prime. And then you want to prove that the W, which minimizes the loss function we were talking about originally, actually is equal to some linear combination of our original data points. And then we just write everything in terms of dot products and substitute. hey, x prime for x transpose x transpose x prime. So we didn't really talk about how you pick a kernel, right? I gave some examples of kernels, and that's sort of a much more hairy problem, right? If you have a nice visualization or intuition for your problem, and have some sense in which, hey, if I project my data in this way, I suspect it'll be easier to separate. That's one way you can actually, that's one way you might actually have some sense as to like what kernel you should choose. But you know, the sort of, you know it when you see it paradigm of like, does this kernel work well? Well, the short answer is, if you use this kernel and you see that you can get low loss, right? And that, you know, the decision rule you actually come up with does a good job generalizing to new data, then you can say the kernel works reasonably well for your problem, right? But there's not sort of a really simple tried and true method for picking the right kernel for your particular problem. That's quite data dependent. And because I have 1 or 2 more minutes, I do want to say one more thing about support vector machines, right? So as I mentioned at the beginning of lecture, right, we said something about SVMs, or at least this presentation of SVM, sort of just saying, here's a loss function, right? In this case, hinge loss. Here's a set of possible decision rules. Right, linear separators. And then, you know, minimize loss over this set of decision rules, right? So there is some interpretation, right? So this doesn't really do any of the modeling of our joint distribution between x and y that we did in most of our previous lectures, right? For least squares, we sort of posited this idea that yi was equal to xi transpose w plus some Gaussian noise, right? That was the process by which our data was generated, right? For some xi, we assume that it was actually generating the y in this linear way with some Gaussian noise, right? And we haven't made any kind of assumption today about how y and x are related, right? That wasn't how SVMs popped out, right? But you know, maximizing the margin, where the margin is, you know, we sort of have the equal amount of margin on both sides of the decision rule, is suggesting that we have some belief or reason to believe that our data is sort of symmetric around the decision boundary, right? Okay, so that's all I wanted to say today, and I'll stick around for a couple minutes, and I also have office hours at 11. Thanks.
Can I ask a question?
Yeah.
Yeah. So the original optimization problem is to optimize the norm, and I wonder, are we change it to dual problem to solve it?
Sorry, say that again. You broke up a bit.
So like are we using the dual problem, transfer it to a dual problem to solve it?
So you certainly can, right? And as was sort of alluded to on one slide, you can think about this problem in the dual and do coordinate descent to solve it. We didn't really talk much about duals today, even though there's a really elegant theory of duals that looks particularly nice when thinking about support vector machines. But I decided that was sort of beyond the scope of introducing SVMs. Not that it's not like a good way to think about it, just that like you can get a lot of intuition without thinking about the dual.
Okay, but and we can solve it without dual also, right?
Yeah.
Okay. I previously learned solving it by duals, and I was like wonder that.
Yeah, you can also do it directly on the primal.
Okay, got you. Yeah, thank you. That answered my question.
I have a question.
Yeah.
Can the margin be unequal for two groups of data? Say if you have more than two groups of data.
Yeah, so we didn't talk today about more than two groups of data, and we've basically like swept that problem under the rug for other settings too, right? Also for logistic regression.
Right.
There are both sort of notational convenience reasons why, right? In the sense that like it's notationally very nice to be able to use yi as being in -1, and being able to look at yi xi transpose wi in a lot of our loss functions, right? That's like a nice representation to play around with. It's also a somewhat more complicated problem, right? So if we're just thinking about linear separators, for example, right? The question becomes like, okay, do I draw a linear separator? Like how exactly do I define the region in which I classify points as belonging to class 1, 2, 3, 4, 5, right? It's very simple when I only have two classes, right? I have one decision rule, below it positive, above it negative, or the other direction, right? When I have 5 classes, right? I can certainly think of sort of like the simple question of I'm trying to learn a decision rule to separate one from everything else.
Right.
But then the question is sort of, do I want to do that separately for each of the classes, or should I do something else? Right? It's a somewhat more complicated problem. Not like insufferably so, right? Not so much more so that you couldn't do it. It's just more complicated to describe for a few reasons.
My question was also for even for two classes. Like, do we ever have like unequal margins? I don't know.
So yeah. So when the data is separable, no, right? When the data is not separable.
And by separable, you mean linearly separable?
Yeah, I mean linearly separable. I'd have to like think about the math about like whether it pops out of that optimization that the like, I think not, but I'm not sure that sort of the amount of violation on the left and the violation on the right sums up to the same. Maybe it is true, because otherwise I can imagine how I would prove it if it's true, but I can't do the math off the top of my head.
Okay.
Kevin, do you happen to know the answer without like looking at the linear algebra?
I didn't quite understand the problem. The question is: it the sum of the CIs? Is that equal to?
Are the sum of the CIs on either side of the, like basically the ones that?
Oh, are they equal?
I mean, they might be. Like I could imagine that popping out of the optimization, but I don't know. Okay, good. It wasn't something obvious that I. Yeah.
Thank you.
All right, I will be back online in about half an hour for my office hours.